In this example, we're being asked to find the antiderivative function f of x if the derivative function and initial condition are given. Now, the fact that we have initial condition given means that if this is our initial condition at some point, it allows us to solve for the plus c. Okay, so we're going to end up with plus c. We need to solve for that. Now, this is called a differential equation. When you see these, basically what's implied is we're being asked to integrate this and find y. But I'm going to include an extra step here. I'm going to just algebraically separate dy and dx. Now, you don't need to do this, but I just want to show you that these are algebraic pieces, and we can do things like this. We can move them around algebraically like this, and we have an equation. And if I take the integral or sum up, okay, so sine x times dx is a rectangular area, I can sum that up, and I'm going to get all the changes in y. And as long as I do it to both sides of the equation, this is still equal. So I'm not breaking any fundamental laws of math of balance here. So what did I do? Well, you don't really need to do this right now, but this is something we're going to end up doing a little bit later on. So I just show you how this looks like. And we kind of been skipping this step, but notice that it's actually consistent. What we're doing is then, if I add up all those changes in y, I get y. And then I end up integrating the sine x. So we kind of skipped this step. We just kind of jumped from here and just said, well, we know that we're supposed to find this. There is an actual algebraic process to do this, and it is algebraically consistent as well, the steps I've done. You may not understand it, and we'll go over those again later, but we've just kind of been skipping this step and jumping from the differential equation straight to the integral, and that's okay for now. So I'm going to find the antiderivative function of sine. It's going to be negative cosine, and we're going to have plus c. And because we have an initial condition, the 0, 1, I can actually solve for the plus c. Okay? This plus c is something I need to solve for, and I can do that by just plugging in y is 1 equals negative cosine x I've been given as 0, and then I'm solving for this plus c. Well, working this out, cosine of 0 is going to be 1, so I get 1 equals negative 1 plus c. That means that c, when I solve for c, c is equal to 2. And so I now have not only found the antiderivative, but I found the actual antiderivative that passes through that point 0, 1. So I have the y function that I'm looking for. Y is equal to negative cosine x. And then instead of a plus c, I actually know that the vertical shift of this cosine graph is going to be plus 2 to make it fit that point. So again, just if you weren't sure about what happened here, this step, don't worry about it because we've been really just skipping that step. But later on, we're actually going to do that step, and we'll go through a little bit more detail. For b, we'll just jump straight to that step. We're going to solve for y, okay, which means I have a derivative. That's my derivative. It implies I'm going to solve for y, which is my antiderivative. So I'm going to put it in this form like this. And there's a dx in there as well. And again, if you're wondering where that dx came from, if you kind of follow the steps back here, that would kind of explain where my dx came from. Okay, so sorry, I had plus e to the 2x times dx. And it's actually a times, and that's actually a factor. So solving for y, I'm going to anti-differentiate 1 over x. This is not power rule. This is that exception to the power rule where I use log. Okay, normally I would try power rules when I have these fractions with x to some power. Here I'm going to anti-differentiate e to the 2x becomes e to the 2x, but because of that extra times 2, I need to remember to divide by 2, and then I have to remember that there is a plus c involved in here. Okay, so there's this plus c, there's this plus c, and that plus c is going to be solved for when if I have a point. In this case I do. I've got a point x and y coordinate, so that's going to allow me to solve for the plus c. So plugging in that coordinate, y is e squared is equal to log, that is going to be 1. I'm plugging in 1 into here, plus e to the 2 times 1, and that's going to be divided by 2, plus c, and this is going to allow me to solve for plus c. So working this out, I get e squared is equal to log 1 is 0 plus e squared over 2 plus c. Solving for the plus c, I get 1 e squared minus half e squared leaves me with positive 1/2 e squared over 2. So now that I solve for the plus c, I can write my equation for y, for the solution to this differential equation is going to be y equals log x plus e to the 2x over 2. And then instead of plus c, I know the plus c is actually e squared over 2. Okay, so this represents the solution, and not only solution, the specific solution to this differential equation that passes through this specific point. So this is the specific solution to the differential equation that actually goes through that point.